In today's class, we are going to continue on looking at forces within a molecule. This is also known as intermolecular forces. And we are going to start off by making sure that we remember what is the difference between a polar and a non-polar molecule. We can differentiate between these things by looking at their electronegativity and calculating the difference in electronegativities between two sides of the molecules. Anybody Lord of the Rings or Hobbit fans? Okay, so you understand the comic a little bit? Okay, can you please pick to your worksheet? It was a 2-pager that you got yesterday. On the first side, you were comparing two molecules. And then on the second side, you have this determining polarity work. If you have not finished these first 8 questions, please take a moment to do so right now. In order to classify a molecule as being polar or non-polar, you need to begin by looking up the electronegativities of the number. This information is found on your periodic table, right above the symbol. The higher the element is on the scale, the more it will hog the electrons. Yesterday we watched a video and I asked you to copy down a graph which looked at electronegativity difference and classification. There is a difference of 1.0 between these two sides of the molecule. This first one is going to be a polar covalent molecule. In the second one, you have a difference of 0.8. It will also be a polar covalent molecule. This one looks a little bit strange. That is because, if we were to draw it out, it looks like this. Oftentimes, the first element is the central atom of the molecule. If it starts with hydrogen, not likely, because hydrogen can only connect with one other thing. So if this is 2.2 here and 2.6 here, the difference between these two is only 0.4. That means that these electrons right here are going to be shared fairly equally. If I compare these two electronegativities here, there's only a difference of 0.8, which means these 6 electrons here are also fairly equally shared. We would not compare this electronegativity with this electronegativity because hydrogen and nitrogen are not sharing any electrons. So it looks like it should be a polar covalent molecule, but it's non-polar.
N is 3.0.
Oh, I was looking at the one above it. I wrote down oxygen. Thank you. There we go. Question number 4. The difference between the two sides is 1.4. This makes sulfur hexafluoride a polar covalent molecule. Question number 5. The difference between these two sides is 0.8, so it is polar covalent. With this molecule, there's only a difference of 0.2. The electrons are going to be shared fairly equally. This is a non-polar covalent molecule. In the arsenic trihydride, there's no difference. This is 100% equal sharing of electrons within its structure. This one looks a little bit strange. So what I'm going to do is draw it out so that it looks a little bit easier to So the core of this particular molecule is 2.6, and each fluorine is at a 4.0. It's the one that hogs the electrons the most. So that means that fluorine is going to hog this pair and this pair. And those are going to create slightly negative ends to the molecule. Chlorine is 3.2 and 3.2 here. It's only a difference of 0.8. So it just barely meets the requirements of a polar covalent molecule. Just barely. And once again, this is going to be slightly negative on the ends because the chlorine is pulling the electrons towards it, and those electrons are spending more time around that side than the others. How did you do with these questions? You're doing okay with them? Kind of, sort of, okay.
It's just the 3 ones that.
Sorry, I didn't hear that. I'll get a little bit closer.
It's just the ones that have 3 that are.
When you have 3, I suggest trying to draw it out, and that might make it a little bit easier to see.
So can you classify the whole thing as like nonpolar or polar when there's 3 steps?
I wouldn't give you a molecule like that at this point, but yes.
How would you do that?
Oh. So a molecule that would do that, I believe, is acetic acid. Also known as ethanoic acid. This is getting more into the carboxylic acids, which is another category of organic compounds. So first of all, this would be an unfair question because we didn't go that deep. If you decide to go on in chemistry, you usually hit organics in your second year. And that's when you learn about the 7 other categories. In order to do this one, you have no choice but to draw it out. Then once you've drawn it out, you can put the electronegativities. So the electronegativity of carbon is 2.6 and 2.6 here. And then over here is, sorry, it's 3.4. And then hydrogen is 2.2. If you look at this side of the molecule, so we're going to start with this carbon first. 2.2, 2.6, 2.2, 2.6, 2.2, 2.6. This is a nonpolar side. If you look at the other side, it's a difference of 0.8. That's just barely meeting the requirements for a polar side. And so you would have a charged side to one side of the molecule but on the other side, no. When we use these in redox reactions, and you start assigning things oxidation numbers, this one is obese Taruka, because you have to look at the electronegativities to figure out the oxidation numbers. So even then, we didn't go as far with the redox as we could have. Again, that would be probably in your second year that you would start to dig a little bit more deeply into complex molecules like this. Does that answer your question? Okay. You're not going to be expected to work with molecules that have one side nonpolar and the other side polar. It's going to be clearly all nonpolar or polar. They can reserve the right to confuse you next year. Okay. One of the reasons why we are so interested in polarity is because of solubility. There is a rule that says like dissolves like. Water is a polar substance. Salt is an ionic compound. Salt has a fully positive charged sodium ion and a negatively charged chloride ion. Water is polar. Oxygen hogs the electrons. Because it hogs the electrons, you have a slightly negative side to water and slightly positive ends to water. Because of this, it literally rips apart this ionic compound. This negative side is going to be attracted to the positive sides of the water molecule. This positively charged sodium is attracted to the slightly negative side of oxygen. So polar molecules will dissolve with polar molecules. Nonpolar molecules will dissolve with nonpolar molecules. How many of you are planning to do biotherapy next semester? Awesome. One of the labs that we do is to look at chlorophyll, which is the pigment in plants that makes plants green. It captures the sun's energy and it drives photosynthesis. If I put this leaf into water to try to extract the chlorophyll, it won't work. The reason is the chlorophyll is a nonpolar molecule and water is a polar molecule. I can stir that leaf in the water as much as I want. The chlorophyll is not going to come out of the leaf. I have to find another non-polar substance so that the chlorophyll will dissolve, which just happens to be ethanol. 99% ethanol. Yeah, you know what that is. Okay. So I actually have to rip apart the leaves, heat up the ethanol, then the chlorophyll will be extracted from there. That's something that I usually do for the students because it's really fussy and it takes about 2 hours to do. I'm going to switch computers and show you an animation of this. Now that you know a little bit more about the chemistry context of polarity, does this comic make a little bit more sense? Help, I'm dissolving, but bears are insoluble. That's easy for you to say. You're not polar. Oh no, understanding the science teacher's sense of humor. can deliberately choose which solvents that we are using when we try to mix something. We make the decision based on things like polarity, non-polarity, in order to increase our chances of dissolving success. Because of the way electrons are either transferred or shared within a molecule, this leads to attractions between different water molecules. One of the very most important types of interactions that I can teach you about is what we call dipole-dipole. An example of this is hydrogen bonding. Di means what? Two poles. What that's referring to is when you have one molecule which has two poles, so that's slightly positive, slightly negative, slightly positive. This is one dipole. And if we have another one of its kind, that also has oppositely charged ends, or is a dipole, then we can have an interaction between this molecule and this molecule. It's not the same type of a bond as the ones holding the O's and H's together within the water molecule. It is a weak bond between two different water molecules. So hydrogen bond occurs when hydrogen in one molecule is attracted to something in another molecule. It has to be oxygen, nitrogen, or fluorine, because those things are higher on the electronegativity scale. Priscilla's done biology 30 already, so let's see if she remembers why this is probably one of the most important things I can teach you about. No? Break the science teacher's heart. It's what holds the DNA molecule together. And the DNA molecule is basically your genetic instruction booklet. When we show a hydrogen bond, we don't use a straight solid line. We use a dashed line. This dashed line shows you an interaction between molecules rather than a bond within a molecule. Okay, I need to switch again. What are your questions about hydrogen bonding? Really? None at all? Water has amazing properties, and those properties can be explained using hydrogen bonds. Compared to a lot of other covalent compounds, water has a very high melting point. 0 degrees Celsius doesn't seem like it is a very high melting boiling point, but a lot of the gases, for example nitrogen in the air, become a gas at a very, very low temperature, which means they have to melt at even a lower temperature than that. So water's high melting point and boiling point can be explained by the presence of hydrogen bonds. Do you remember how the movement of a gas is different than the movement of a liquid? So particles in a liquid are vibrating and they're turning around. When it becomes a gas, those particles have to start traveling in straight lines. And then they bounce off each other as they strike each other. In order for those water molecules to move independently in those straight lines, all of these hydrogen bonds have to be broken. That takes energy. That is the reason why water has such a high melting and boiling point. When you drink soda with a straw, you have probably noticed that so you have your glass here and you have your straw here. If you take a look at the fluid in the straw, it's actually higher than the soda that's in the glass. The reason for that is because these opposite charged ends are actually being attracted to the straw and are starting to travel up the straw because of attractions. Water can stick to other objects because of these oppositely charged ends and itself. Have you ever seen a water spider or a water strider walk across the top of the water? That's called surface tension. And the reason why that exists is because the water is being attracted to the particles beneath it, and it creates almost like this skin across the top, which insects manipulate. Water is really unique because it is less dense in its solid form. This is not the norm. Oftentimes, water is far more dense, a substance is far more dense than its own liquid. And the reason for that is when water starts to freeze, it's going to be attracted to other water molecules because it's traveling so slow. And that's going to force the water particles to spread out because of attraction and repulsion. Thought I put a picture in here, so I'm just going to go to the internet here. So that's what the water molecules look like when they've been forced into a certain shape because of these attractions between slightly negative and slightly positive ends of the water molecule. This takes up more space than liquid water particles that are able to move around and break these attractions. Because of that, water floats. Solid water floats. How would life on Earth be different if water sank when it froze? Ice fishing would kind of suck. What would happen is, so we have our lake here, and that's a fish, okay? We can pretend that's a fish. If solid water was more dense than liquid water, as the water froze, the ice would sink to the bottom of the lake. Then more liquid water would freeze, and sink to the bottom of the lake. And you would actually have a lake that would be frozen from the bottom to the top, which would mean by the time it was safe enough for you to ice fish, you would basically be drilling for fishicles, because the fish would be solid frozen in the lake. Then, when the lake melted in the spring, that water would pool on the top. Light only penetrates about 3 to 4 meters, which would mean the bottom of your lake would never finish thawing out before the next cold season. Yeah, so water is a pretty amazing molecule, and it all comes down to its polarity. It also means that it has a very high specific heat capacity. We have to really disrupt those hydrogen bonds in order to make water change temperature. That is really, really good because you are 75% water. If you had a fever and water had a low specific heat capacity, your organs would be damaged every time you would be sick because you wouldn't have the water to absorb the heat. Since water has a high specific heat capacity, it has an enormous ability to absorb water or absorb heat and not change temperature. This is the reason why it is so important that you stay hydrated when you have a fever. Dehydration is really risky, especially for really, really young children. Some of you have babysat, or maybe you have a really young sibling, and you know that if a young child does not want to drink water, they're not going to. Good luck with that. Okay, we have a few more intermolecular forces to talk about. And I'm not going to finish that today, so that means that after the quiz I'll finish this up. We'll preview the video, and that will be the end of the class. Tomorrow's quiz is from where we left off on the last quiz. On the last quiz, you were drawing alkane and alkene structures. So it will include branched alkanes, alkynes, the reactions, Vesper, and polarity.
Did you finish that second assignment for me?
That's the one that I couldn't print that I put on Google Classroom.
Oh, okay.
So as soon as the class is over, I'll shut down this computer and reboot it and see if that's enough to reconnect me to the printers. But I've tried every printer in the building.
If it doesn't work, I can print it at home too.
Okay.